Hello class, this is lecture 5D, Soil Acidity and Alkalinity. And we are going to identify and discuss the causes of acidification. We'll explain how aluminum toxicity works and its significance. We'll explain how liming works and the chemical reactions that take place during liming. The different pools of acidity, how soil pH, CEC, and base saturation are all related, and we'll provide some examples of the significance of soil pH. All right, so soil pH is what I would consider a master variable. And what I mean by that is as this variable changes, it has a big impact on a whole range of other soil properties. So it impacts how much nutrients there are available to plants or to microbes. It changes the types of microbes that are present. So you actually see shifts in microbe communities as pH changes. Same with plant communities. CEC can go up and down depending on what the pH is. And there are a whole range of other chemical and physical properties of soil that change as we change with soil pH. And so acidity and alkalinity are really just kind of two ranges of the same scale, this pH scale. And so we have a balance of hydrogen ions and hydroxyl ions. And we quantify this using the pH scale. So if you remember back to chemistry, pH stands for the negative log of the concentration of hydrogen. And so as we go lower in pH, we have a lot more hydrogen that's dissolved in water. And as we go up in pH, we have a lot less hydrogen that's dissolved and a lot more hydroxyls. For some context, here is a range of different pHs. And it shows some example soil types and what is normal for a pH for those soils, as well as some other liquids or materials that you might be more familiar with in their pHs. Let me get my pointer going here. All right, so on the lower end we have battery acid, so a pH of around 1. And we don't really have soils that get that low in pH, but we do have soils that can get close to that and around the pH of lemon juice, which is a pH of 2. And so this would be what we call active acid sulfate soils. So these are where we have reduced sulfur that becomes oxidized, produces sulfuric acid, and the result is a very low pH. Vinegar is a little less acidic at a pH of 3. And once we get into coffee and beer, we have pH of around 3.5 to 6, and that would be about what we would expect for forest soils. And as we get into just slightly acidic areas, we get into what would be humid region arable soils. And then at a neutral pH, we have pure water or milk has a pH of 7. And then as we move into drier regions, we get more calcareous soils and even sodic soils. So calcareous soils occur up to about a pH of 8.5, which is about the same as baking soda. And then once you get into sodic soils, if we have a really high amount of sodium, we can have a pH of 8.5 and higher. And so then we're getting into some antacid tablets and even bleach at a pH of 12. So that's kind of the range. So for acidification, there are two processes that promote it. One is the production of hydrogen ions, and the other is washing away of non-acid cations by water that's percolating through the soil profile and leaching away. So the sources of hydrogen ions that are actually producing hydrogen in the soil, it could be carbonic acid and some other organic acids. If we accumulate organic matter, then we're producing those organic acids. So organic matter can actually create acidity over time. If we have nitrogen that's being oxidized, and if you remember back to the nitrogen cycle, this is what we call nitrification. So taking ammonium and nitrous ammonium and nitrobacter convert it into nitrate. And in the process, those 4 hydrogens from the ammonium, 2 of them go into water molecules and 2 of them go into acidity. So we're actually creating acidity as those microbes convert ammonium into nitrate. Sulfur, as it gets oxidized, produces hydrogen. And also plants can acidify the rhizosphere and in the process of taking up cations. And we also get acidity through what we call the hydrolyzation of water by aluminum. So let's focus on these carbonic acids first. So here we have CO2, and if CO2 dissolves in water, it forms H2CO3, which is a weak acid, and that forms bicarbonate and hydrogen. So in other words, CO2 as it dissolves forms carbonic acid. And as we accumulate organic matter, we have a lot of compounds or a lot of these functional groups that will have acids on them, so they'll be protonated, and those hydrogens can be released into the soil solution. And in other words, the hydrogen is dissociating from those functional groups. What can also happen is these organic compounds can complex with base cations like calcium and magnesium, and that actually makes those compounds or those elements more soluble, which can facilitate leaching of those cations. So I touched on this a little bit earlier. So nitrification, again, we start off with ammonium. In the presence of oxygen, nitrous ammonius and nitrobacter are converting this eventually to nitrate. And in the process, we're creating a water molecule and 2 hydrogens. So 2 hydrogens total. So for every 1 mole of ammonium, we produce 2 moles of acidity. And if you look at this, HNO3 is nitric acid. So you could think of this product as a dissociated nitric acid. Sulfur usually occurs with iron sulfides. So iron sulfides are generally precipitated by microbes in a reducing environment. And if we take materials that are high in iron sulfides, bring them up to the surface and expose it to oxygen in the presence of water, then we get iron sulfate and 2 moles of hydrogen and a mole of sulfate. And that is dissociated sulfuric acid. So you can see how oxidation of sulfur could, if it produces a strong acid, you can bet that it's going to produce very acidic soils when this process occurs. Another source of acidity can be plants themselves. In some cases, plants will do this on purpose to provide some benefit in terms of soil fertility. So it might make, say, phosphorus more available as the rhizosphere gets acidified. And that's the case in soybeans and faba beans and other legumes, is as they take in, say, calcium, they are releasing 2 moles of hydrogen. And so here, this tan-colored bar here, this is supposed to be like a close-up of a root. And so as calcium is going into the root, because it has a 2+ charge, that root has to maintain a charge balance. And so it has to exude cations of some sort. And in this case, it is exuding hydrogen. And same with ammonium. As ammonium is taken up, 1 mole of ammonium goes in, 1 mole of hydrogen comes out. So in both those cases, the hydrogen that's produced inside the plant is actually released and it acidifies the rhizosphere. And you can see that in this picture on the left side. We have a faba bean and a soybean, and these are grown in an agar solution. And there's a pH indicator in the agar gel. And as the soil becomes more acidic, the gel becomes more yellow. And you can see in the rhizosphere of the faba bean and the soybean, in both cases, it's becoming more acidic. And if those beans are trying to, say, dissolve some rock phosphate that was applied as fertilizer, then that rock phosphate in a more acidic condition would actually dissolve faster, making phosphorus more available. In the case of corn, corn is taking up a lot of nitrate, likely in this picture. And so as nitrate's taken up, because it has a negative charge the plant has to offset that by releasing a hydroxyl. And so in this case, the plant can actually increase the pH and decrease the acidity. So that's what's happening with this corn picture. So plants, this is a common theme throughout the semester. Plants are not as passive as they seem. They are actively changing their environment around them to their own benefit. Another source of acidity is aluminum. And one issue with aluminum is that it is highly toxic to roots. So not only does it produce acid, which can cause issues, low pHs also make aluminum more soluble, and that is toxic to roots. And the issue that comes from that is it can actually stunt the root growth of plants because it more or less inhibits cell division at the root tips of plants. So that is a problem by itself. Aluminum also hydrolyzes water, and that causes more hydrogen to be dissolved, which lowers the pH. And 1 mole of aluminum, depending on what pH you're starting at, 1 mole of aluminum could potentially create 3 moles of acidity. So in this example, we have aluminum 3+, and notice these are all reversible reactions, but in the first part, if we go to the right, it goes from Al3+ to AlOH2+, and in that direction, water is hydrolyzed. So the hydroxyl goes onto the aluminum, and then 1 hydrogen is released into solution. And that happens at a pH of around 5. And then that can happen again. So AlOH2+ hydrolyzes water, creating AlOH2 1+, which produces 1 more mole of hydrogen. And that happens at a pH of around 5.1. And then that can happen a third time where AlOH2 1+ turns into AlOH3. And that hydrolyzes 1 more mole of water, producing a mole of acidity. And that happens at a pH of around 6.7. And so, so these 3 reactions, if we start at Al3+, it can potentially produce 3 moles of acidity from 1 mole of aluminum. Now, going back to the point about aluminum being toxic to roots, if we have aluminum in too high of concentration, then we end up seeing a deformed root tip like you see on the top right compared to a healthy root tip on the left. And then these other pictures show seedlings growing at different concentrations of aluminum. So more dissolved aluminum on the right side in this picture, less aluminum dissolved on the left side. And so there's more cell division at the root tips, allowing the root systems to become larger. And same goes for the picture on the bottom left. Had the most aluminum on the left side, the least aluminum on the right. And you can see how much bigger both the root systems, especially the root systems, but also the plant stems are as we decrease in aluminum content. So aluminum has a big impact on the root systems of plants. All right, so soil acidification, as we have these sources of acidity producing hydrogen and releasing that into solution, what that does is creates a situation where there are more hydrogens in solution, and that because the CEC has to stay in equilibrium with what's absorbed versus what is dissolved, those hydrogens are going to exchange with the cations that are on the CEC, and so those hydrogens are displacing cations, making them go into solution, and then if there is excess water, those cations that are in solution can be washed out of the system. So they're lost due to leaching. And as a result, the soil actually becomes more acidic. And so we slowly fill up the CEC with hydrogens. And as a result, the soil pH is going down and the base cations are leaving. And this happens in environments particularly where there's lots of rain, because there's more potential for leaching. Now, looking at the pH of counties across the U.S., you can see where we have more acidic soils. So where we have colors that are this kind of orange color, that's pHs of 4.5 to 6. So most of the southeast going into kind of mid-Atlantic and the northeast. So this area gets lots of rain. And then as we move into the Midwest, so the Corn Belt is mostly neutral pH. And then as we get to drier areas, it's mostly pHs above 8. And so the more rain we have, the more leaching of base cations there are, and as a result, we have more acidic soils. The less rain we have, we generally are accumulating salts, and that causes higher pHs. So lots of rain equals acidic soils, moderate rain equals neutral soils, little rain equals alkaline soils. All right, so for alkalizing processes, these are processes that either remove hydrogen or add hydroxides. So this could be the weathering of base cation containing minerals. So as minerals break down, if they're releasing hydroxides or hydroxyls, then that can lower the pH or increase the pH and neutralize some of the acidity. We can also accumulate some non-acid base cations, and some examples of those are calcium, magnesium, potassium, sodium. And so those can help displace the hydrogen, allowing it to be washed out, but it's only going to really change the pH if we neutralize the hydrogen that is exchanged. And for that to happen, we need to have carbonate or bicarbonate present. And these react, or these raise the pH because they are reacting with water to form hydroxides. And those hydroxides then combine with the hydrogen to produce more water. So I'm going to give you an example. So here we have egg lime, or limestone, calcium carbonate. And the calcium carbonate, when it's dissolved, it will dissolve into calcium 2+ and carbonate. And the carbonate reacts with water, produces bicarbonate and a hydroxide. And the bicarbonate reacts with water again and forms H2CO3 and another hydroxide. And the H2CO3 eventually turns into water and CO2. And that CO2 can then off-gas from the soil out into the atmosphere. And one thing to note is these are all reversible reactions, so they can go both ways. However, this last reaction, because we are removing a product, it drives this reaction to the right, or to the product side. And that drives the reaction above it to the product side, and the equation above that to the product side, and the equation above that to the product side. And so the removal of CO2 during the liming process is what drives the whole process forward to actually raise the pH of the soil. And so 1 mole of calcium carbonate creates 2 moles of hydroxides, which means that those hydroxides can neutralize 2 moles of acidity. We can get a reversal of this if we have high amounts of respiration, where we're actually producing CO2 and causing these reactions to go the other direction. But that's kind of rare. Usually there's enough CO2 removal that we can drive these reactions to the right and get an increase in pH. Our pools of acidity include active acidity, exchangeable acidity, and reserve acidity. So active acidity is what is due to hydrogen that is dissolved and in the soil solution. And this is what we measure directly using a pH electrode. And it is the smallest pool of acidity. The next pool is exchangeable acidity, which includes the aluminum and hydrogen that are on the CEC. And these can be exchanged by other cations, or with other cations. And we measure this by adding a concentrated salt solution. Potassium chloride is most often used. But we would add a concentrated salt solution to a soil, and that would displace the exchangeable cations, and then we would measure the pH again to see how much additional acidity was sent into solution after those exchanges. And the third type is reserve acidity. So these are acid cations that are present in the soil, but they're not readily exchangeable, meaning that they might be trapped between layers of clays, or they're in some position where they can't readily be exchanged with base cations. And generally, as the pH goes up, these aluminum and hydrogen cations that are usually inaccessible, they will eventually be released into solution, bringing the pH back down. So the reserve acidity sort of adds some buffering capacity to the soil to maintain whatever the status quo pH is. This is the largest pool of acidity, but we can really only manage it by trying to remove or neutralize the acidity that is exchangeable or the active acidity first. So we have to neutralize the top two pools to allow what's in the bottom pool to be released into solution. And then we have to go back and re-neutralize the soil again to try to raise the pH. So our pools of acidity, again, we have this residual or the salt replaceable and the active. So the active is what's dissolved and floating around in the soil solution. The salt replaceable or exchangeable is what is on the CEC and can readily be exchanged with cations that are dissolved. And then residual is what is kind of bound up as part of the clays and part of the humus or the soil organic matter. Now, one way we can characterize how acidic a soil is, or the degree of acidity present, is the percent base saturation. And the percent base saturation is a relatively simple calculation. What we're trying to do is calculate the proportion of the total CEC that is filled with what we consider base cations. And how we do that is we would sum all of the CEC that is coming from base cations. So here we have the milliequivalents of base cations per 100 grams of soil, divided by, what the bottom is just total CEC. So that's both base cation or charges from base cations plus the charges from the acid cations in units of milliequivalents per 100 grams. So the bottom is total CEC, and the top is CEC that's filled with base cations. And we take that fraction times 100%, and that's how we calculate base saturation. So our acid cations are hydrogen and aluminum. And then the base cations are everything else. So anything that's not hydrogen or aluminum, we consider a base cation. Calcium, magnesium, potassium, ammonium, sodium, and so on. So let's do an example just to make sure you follow. So what is the base saturation if a soil test on a 100-gram sample resulted in the following composition? 14 milliequivalents of calcium 2+, 2 milliequivalents of magnesium 2+, 2 milliequivalents of potassium 1+, 1 milliequivalent of ammonia 1+, 1 of sodium 1+, 2 of aluminum 3+, and 2 of hydrogen 1+. And so if we add up all of the milliequivalents from all the base cations, so 14 plus 2 plus 2 plus 1 plus 1, we get a total of 20 milliequivalents from base cations. And then in the denominator, we take that 20 milliequivalents from base cations plus 2 milliequivalents from aluminum and 2 milliequivalents from hydrogen, our two base cations. So 4 milliequivalents from acid cations. And so we would have 20 milliequivalents divided by 24 milliequivalents times 100%. And in this example, we have an 83% base saturation for the soil. And that's pretty high. Okay, so to relate that to pH, CEC, and base saturation, we have this figure on the right. And one trend that occurs is as the pH goes down, the aluminum OH2 bind tightly to the CEC. So aluminum OH2 and hydrogen and so on bind tightly to the CEC, and they, as a result, take up some potential binding sites. And so as we have more aluminum and more hydrogen that are taking up binding sites and making them no longer available to be used for cation exchange, we are decreasing the what we call the effective cation exchange capacity. So let me explain this figure a little bit. So on the left on the y-axis, we have the percent of the maximum cation holding capacity. And then on the x-axis, we have soil pH. So going from 3 to a pH of 8. And then the colors here are just showing what percentage of the CEC is being filled with what type of material or what type of cations. So the analogy that I use for this is, again, this is, let me go back. The analogy that I use to explain this is think about parking on campus. We have so many parking spots that are potentially available. And in the summer, the university goes through and they repaint all the parking lots. They put on new lines for all the parking lots. And before they do that, they'll go through and they'll tape off some of the spots where you can't park on it for a couple days, so that they don't have to tow cars out to actually get the parking lot painted. So they'll put cones in the spots, or they'll tape them off with some hazard tape or something. And so they are removing parking capacity in order to do that. If we think about those parking spaces as individual exchange sites, then as we lower pH and we have more aluminum and more hydrogen that are kind of leaving or covering up those spots, then that reduces the capacity to park other cations on the CEC. So the more acidic the soil is, the more aluminum there is, and the more hydrogen there is, and we get bound hydrogen and aluminum, and we also have some exchangeable acid cations. So some of these sites are tightly bound, and we think of that as reserve acidity, and some of these sites are exchangeable, and we call those exchangeable acidity. And so these exchangeable acid cations can be exchanged with calcium and magnesium and so on. But our reserve acidity is what's tightly bound, and that reduces the potential CEC that might be available at a given pH. And once we get below a pH of 5.5, we really start to increase in how much of these spaces are filled with acid cations, and how much are filled with, and decreasing how much are filled with. We are, then the soil CEC starts to fill up with these hydrogen cations and the aluminum, and that decreases the ability for the soil to hold on to CEC. And once you get below 5.5, then most of what's left of the exchangeable sites become filled up with primarily hydrogen. But as we lime the soil and we increase in pH, then we both neutralize some of this reserve acidity, and as a result increase the effective cation exchange capacity. But we're also dominating what is exchangeable with non-acid, or what we call base cations. So how we measure pH? There's a couple ways. The primary way is to use a pH electrode. So if you submit a soil test to a lab, they're generally going to use a pH electrode. Oftentimes nowadays that's done by a robot as opposed to a person doing it like you see here. But we have a soil that would normally be ground up and dried, and then as that soil is processed, they add water to it to make a slurry, and so it's usually like a 1-to-1 ratio slurry of 1 part water, 1 part soil, and they stir that up, stick an electrode, and the electrode measures the active acidity. And so if you wanted to actually get a test done, you could just take a sample, put it in some sort of sample bag, fill out a form, and submit that to a soil testing lab like the K-State soil testing lab. You can also get kits to do this on your own. The kits are sort of expensive. They're more convenient because you get your results right away. but on a per test basis, they do cost more. But here's an example of just one you can find out online. And these usually work by, you still make a slurry, but then most of them work by having you sprinkle some sort of powder on the soil slurry, and that powder will change color. And then you use some sort of color reference card to determine what pH the soil is. There's also soil pH strips that are also relatively expensive, and not quite as accurate as a pH test, but they do work. So I did mention that soil pH is a master variable, and one of the things that it can impact is fertility. And so what it does with fertility is it makes nutrients more or less available depending on what pH you're at. Now there's a lot of kind of hand waving and generalizations that went into this graph, but what you see, but it does work in most situations. There are certain situations where it doesn't apply as well, but in most soils, this is what we experience. And how this graph works is the thicker these black bars, the more of that individual nutrient is available at a given pH. And so phosphorus, for example, is most available at a pH of around 7 to 7.5. As we go lower in pH, there are more iron and aluminums present, and those will actually fix phosphorus and make it less available. And as we go higher in pH, there's more calcium present. And the more calcium that's present, the less phosphorus is available, because calcium will also precipitate phosphorus. And so there's different reactions taking place, but what we notice is there are a certain pH range for each of these nutrients where we see the most plant availability that occurs. And one thing to point out is there's sort of a Goldilocks zone of around pH 6.5, where across the board, pretty much every nutrient that a plant would need is either at or close to its maximum availability. And so usually we have a target pH of around 6.5, sometimes more or less than that. But for most plants that we grow, a pH of around 6.5 is usually best. And if you just look at all the different nutrients, they're all more or less available at that pH. Now another example of that is yield. So some plants have a different sort of Goldilocks zone. And so to show you how that works, corn and wheat both have an optimum pH of around 6.8. And so this table is showing the relative yield of these different crops relative to the pH where they had the highest yield. So the highest yield for corn was pH 6.8, highest yield for wheat was 6.8. So for corn, for example, if we have a soil pH of around 4.7, we would only get a yield of 34% of what we would have had our soil been managed to be a soil pH of around 6.8. Wheat is more tolerant of pH than corn is, but we still get a big yield decrease as we get more acidic soils. Barley does not like acidic soils, so barley prefers a really high pH, it's pH 7.5, and as we decrease pH and get more and more acidic, barley really drops off in yield. Soybeans like pH of 6.8, and alfalfa likes pH 6.8 or higher. So alfalfa needs a lot of calcium, and so calcium is most available at pHs of 6.8 or higher. So depending on what you're trying to grow, it is important to realize what the optimum pH is and then manage your field appropriately. For a turf grass example, there are ranges of different preferred pHs that vary by the grass species. So fescue has actually kind of a big range, so 4.7 to 8.5. So just about any regular pH that we would experience, fescue is going to do okay. Zoysia likes slightly acidic soils. Bermuda grass, slightly acidic, but does okay up to a pH of 7.5. Ryegrass has kind of a narrower range, 6 to 7. Buffalo grass 6 up to 7.5. So, so again, in this situation, it's not just agricultural crops. It's also things like turf. There is a target pH depending on the particular variety or particular species. So it's important to kind of consider what you're trying to grow when you're managing soil pHs. There's also other applications of soil pH. So pH can greatly impact how different pesticides are absorbed by the soil, how toxic they are to plants, how fast they break down, and also how long they persist in the soil. So it's really important to know what the soil pH is when you're trying to figure out dosing rates or application rates for different pesticides. And I have one case study that we're going to end this lecture with. So in South Central Kansas, these are the counties that are some of the top wheat producing counties in the state. But a couple of decades ago, across a bunch of these counties, they were experiencing really poor wheat growth, and it was especially variable in low pH soils. And the growers in this area described these conditions as their wheat plants were being droughty. So it looked like they weren't getting enough water, which can be an aluminum toxicity problem or symptom. They also showed nitrogen and phosphorus deficiency, even though the soil test showed that there should have been plenty of available nitrogen and phosphorus. This area was using high rates of ammonium nitrogen, which is an acid-forming fertilizer. And also, just because this region was developed from limestone soils, traditionally there wasn't much limestone added because the soils were neutrally alkaline to begin with. But over time, as ammonium was applied to the soil, acidification occurs, and it was slowly lowering the pH. And as this occurred, then the pH dropped, and as a result, that actually raised the soluble aluminum levels. And so what ended up happening was they had acidic soils that were caused by fertilization that eventually increased the aluminum availability. And in this case, aluminum, or in all cases, aluminum at too high a concentration becomes toxic to plant roots. And so they were trying to grow a wheat crop with a severely stunted root system on their wheat plants. So this is an example of the need to manage soil pH so that we can avoid some of these issues that we get with really acidic soil pHs.